At the dawn of the Second World War, the skies above Europe and the Pacific were arenas of rapid innovation and brutal attrition. Each nation's aircraft represented not only its industrial strength, but also its philosophy of warfare. By the early 1940s, Allied and Axis engineers were racing to define the next generation of aerial dominance. In the Pacific, the Japanese Zero reigned supreme, light, agile, and deadly at low speeds. Its Nakajima Sakai engine provided reliability and reach, giving Japanese pilots a fearsome advantage in the early years of the conflict. Against this, the Allied forces found themselves struggling to field a fighter that could both climb and dive with power, while also enduring the long distances of oceanic warfare. The Americans faced a particular challenge: distance. Any aircraft operating in the Pacific had to cross immense stretches of water, often without escort, and arrive with enough fuel to fight and return. This logistical reality shaped not only the aircraft designs of the United States, but also its engine philosophy. Range, altitude, and reliability were everything. In the late 1930s, as Europe plunged into war, American engineers at Allison began work on an engine that would change how power could be delivered in flight: the Allison V-1710. It was a bold concept, a liquid-cooled V-12 engine that could be adapted to a range of aircraft, from single-engine fighters to twin-engine interceptors. At a time when most American designs favored air-cooled radials, the V-1710 stood apart, a compact, high-performance power plant built for altitude and speed. But on its own, the Allison lacked something vital. It needed a way to breathe efficiently at the high altitudes where performance mattered most. The answer came not from Allison itself, but from General Electric, a company experimenting with exhaust-driven turbo-superchargers, a technology still in its infancy. When these two engineering worlds collided, they created one of the most sophisticated propulsion systems of the war. That fusion would find its perfect home in the Lockheed P-38 Lightning, a twin-engine interceptor unlike anything seen before. With its twin booms, central nacelle, and twin Allison engines, each boosted by a General Electric turbo supercharger, the Lightning became a mechanical symphony of innovation. While most Allied fighters relied on mechanical superchargers alone, the P-38 used an exhaust-driven turbine to compress the intake air, maintaining power as the aircraft soared into the stratosphere. This was not just an improvement, it was a revolution in engineering logic. By late 1941, as the Pacific War erupted, the Lightning began to prove itself. Pilots described its climb rate as astonishing, its high-altitude performance unmatched. It could intercept the bombers and outdive any Japanese fighter, a combination that baffled the enemy. Meanwhile, Japanese engineers, accustomed to lightweight simplicity, viewed the Lightning as an impossibly complex machine, heavy, over-engineered, and beyond the capacity of their factories. Yet by 1943, when a damaged P-38 was captured in relatively intact condition, they would discover just how advanced it truly was. At the Tachikawa Air Technical Arsenal, the heart of Japanese aeronautical research, engineers dismantled the aircraft piece by piece. What they found inside the Allison V-1710 and its paired General Electric turbocharger would astonish them. For the first time, Japan's finest minds confronted the depth of Allied metallurgy, machining precision, and thermal control. This was not merely a study in enemy technology, it was a moment of revelation. The captured Lightning showed Japan's engineers a glimpse of industrial power they could not replicate. The story of that engine, the Allison V-170, and the twin turbocharged heart of the P-38, is a story of mechanical mastery, of human ingenuity, and of how engineering supremacy shaped the outcome of the air war in the Pacific. The Allison V-170 was not born from war. Its origins stretch back to the early 1930s, when the U.S. Army Air Corps was still experimenting with concepts of altitude flight and high-speed performance. At that time, the United States lagged behind Europe in both aviation engine design and production capacity. Rolls-Royce and Daimler-Benz led the world in liquid-cooled V-12 technology. While American manufacturers remained focused on rugged air-cooled radial engines, Allison engineers, working from their plant in Indianapolis, sought to change that. They envisioned a liquid-cooled engine capable of sustaining power across a wide range of altitudes. The V-1710, first run in 1933, was built with an emphasis on modularity, a design principle that allowed it to evolve with the demands of new aircraft. It had a single overhead camshaft per bank, 4 valves per cylinder, and was built from light aluminum alloys to save weight. By 1939, the engine was ready for operational testing. Producing around 1,000 horsepower, it offered an excellent power-to-weight ratio, but without forced induction, its performance would drop sharply above 15,000 feet. That's where General Electric's turbo supercharger entered the story. In 1939, GE's engineers were experimenting with capturing exhaust gases to spin a turbine, compressing the intake air before it entered the engine. This approach allowed the engine to maintain near sea-level manifold pressure, even at high altitude. It was an elegant, complex solution that required not only advanced metallurgy, but also precise thermal management and fluid dynamics. Lockheed engineers, led by the visionary Kelly Johnson, saw the potential instantly. They proposed installing 2 V-1710 engines on a twin-boomed airframe, each coupled to its own turbo supercharger and intercooler system. The result would be a twin-engine fighter that could outperform anything in existence. The P-38 prototype. When it first flew in 1939, the P-38 astonished observers. It reached over 400 miles per hour in testing, faster than any U.S. fighter had ever achieved. But its complexity was daunting. Managing the dual turbochargers, intercoolers, and fuel systems required engineering precision at every level. The marriage of the Allison V-1710 and the GE turbo supercharger was not just an engineering partnership. It was a merging of two philosophies. Allison provided raw mechanical strength, GE delivered breathing power at altitude. Together, they turned the P-38 into a machine capable of operating in thin air, where Japanese aircraft could barely fly. It was this blend, industrial scale, metallurgy, and design, that would later leave Japanese engineers speechless when they encountered it firsthand. The true genius of the Allison V-170 lay not only in its power output, but in the way it sustained that power at altitude. In the Pacific theater, altitude meant life. Japanese Zeros and Oscars were unmatched below 20,000 feet, but their engines, optimized for low-weight combat, lost significant power as oxygen thinned. In contrast, the turbocharged P-38 could climb to 35,000 feet and still deliver near maximum boost. Each of its twin V-1710 engines used an exhaust-driven turbine that fed compressed air through a complex system of ducts and intercoolers before entering the engine's intake manifold. The system maintained manifold pressures as high as 45 inches of mercury, even at extreme altitudes. Technically, the challenge was immense. The exhaust gases reached temperatures exceeding 1,200 degrees Fahrenheit, requiring heat-resistant alloys and precision machining in the turbine housing. General Electric's engineers developed nickel-chromium superalloys that could withstand the thermal stress without distortion, materials Japan simply did not possess in sufficient quantity or quality during the war. To control all of this, the pilot managed multiple instruments: turbo boost, mixture, throttle, and propeller pitch, a delicate balance of power and temperature. Experienced pilots learned to synchronize the turbo's whine into harmony, listening for changes in tone that signaled imbalance or overboost. The result was extraordinary. At high altitude, the P-38 could intercept enemy bombers, conduct photo reconnaissance deep into enemy territory, or dive faster than almost any aircraft of its era. Its engines gave it a speed advantage that Japanese fighters could neither match nor pursue. For Japanese pilots accustomed to seeing Allied aircraft falter above 20,000 feet, the Lightning was something new. And for Japanese engineers, it was nothing short of stunning. When the P-38 entered service, it was unlike anything the U.S. Army Air Forces had ever deployed. 2 engines, counter-rotating propellers, tricycle landing gear, and a central nacelle housing the cockpit and armament. Its power came from the twin Allison V-170, each driven by its own GE turbo supercharger, a design that gave it redundancy, speed, and resilience. In the Pacific, the Lightning quickly established its legend. From Guadalcanal to the Philippines, P-38 squadrons dominated the skies. Pilots like Richard Baum, America's top-scoring ace, used the aircraft's climb rate and firepower to devastating effect. Where other fighters struggled in thin air, the Lightning surged. Its performance was unmatched at altitude, It could dive from 35,000 feet at speeds exceeding 400 miles per hour. Japanese Zeros, built for agility, simply could not follow without risking structural failure. The P-38's Allison engines, supported by their turbochargers, allowed it to climb away or engage at will. Even when damaged, the twin-engine design gave pilots a margin of safety unmatched in single-engine fighters. Countless airmen returned home on one functioning Allison engine, the other feathered, the turbo still howling on the surviving side. To Japanese observers, the lightning was terrifying. It appeared suddenly, struck with precision, and vanished into the upper sky. For the Imperial Japanese Army Air Force, which relied on lighter, less durable fighters, the lightning represented a new kind of warfare, one that combined altitude dominance with industrial power. Behind its performance lay not just design brilliance, but the mastery of thermal control and material science. The turbochargers operated at temperatures and pressures few Japanese engines could withstand. Each intercooler assembly, tucked into the booms, absorbed immense heat to prevent detonation. Every element of the system, every pipe, bearing, and valve, was a testament to industrial sophistication. In 1943, when Japan recovered an intact P-38, it was sent to Tachikawa Air Technical Arsenal for evaluation. What followed there would become one of the most intriguing and lesser-known technical stories of the entire Pacific War. In late 1943, deep within Japan's most advanced aeronautical research facility, the Tachikawa Air Technical Arsenal, a small team of engineers gathered around the wreckage of an American P-38 Lightning. The aircraft had been forced down in a remote area, remarkably intact. Its capture was a prize beyond measure. The Japanese engineers began dismantling it with meticulous care. The airframe itself puzzled them, heavy, robust, built for durability rather than agility, but it was the engines that drew their deepest attention. The twin Allison V-1710, each paired with its own General Electric turbo supercharger, next level of mechanical integration. The first shock came when they examined the turbocharger assembly. The concept was understood, they knew what a supercharger was, but the execution was astonishing. The turbine wheel, spun by the engine's exhaust, drove a centrifugal compressor that forced dense, cool air back into the intake. The Japanese engineers noted the precision casting and machining of the turbine blades, the high-temperature alloys, and the smooth aerodynamic contouring of the ductwork. One engineer, according to post-war recollections, remarked that it would not be possible to produce this with our machines. Their factories, strained by war, lacked both the materials and the precision lathes required for such close tolerances. They noted the cooling system, liquid-cooled blocks fed by radiators and intercoolers positioned deep within the twin booms. Every pipe and fitting seemed calculated for efficiency. Even the routing of oil and coolant lines reflected an understanding of thermodynamics that impressed the examiners. The Allison cylinder heads were of particular interest. The metallurgy, high in nickel and chromium, gave them strength and heat resistance that the Japanese metallurgical industry could not replicate. The fit between pistons and cylinders was so fine that even after months of exposure, the internals remained almost uncorroded. What most amazed them, however, was the integration of systems. All functioned as one cohesive unit. To replicate it, Japan would need not just blueprints, but an entire industrial revolution. When the examination concluded, the engineers at Tachikawa compiled their report. The conclusion was sobering. While they could understand the principles, the execution was beyond Japan's wartime capability. Their engines, while ingenious in simplicity, could not match the precision metallurgy and high-temperature tolerance of the American system. The captured Lightning was eventually destroyed in an air raid before it could be fully flight tested, but the impression it left endured. The engineers who studied it spoke of the encounter years later, not with bitterness, but with admiration. They had seen, in the Allison V-1710 and its turbo supercharger, the embodiment of Allied industrial mastery. To them, it was not just an engine, it was proof that America's power lay not only in numbers, but in the science of engineering itself. By mid-1943, the Pacific skies had changed. The once dominant Mitsubishi Zero was now meeting aircraft that could neither outrun nor outclimb. Among them, none intrigued the Japanese more than the Lockheed P-38 Lightning. Its speed, its twin-boom shape, and its ability to engage at altitudes where the sockeye engine gasped for breath were bewildering. Reports from pilots returning from combat over the Solomons and New Guinea spoke of a twin-tailed American fighter that struck from great height, fired devastating bursts, and was gone before they could react. The Japanese military intelligence divisions became obsessed with this machine. They called it the twin-tailed devil. Its performance figures, gleaned from combat reports, were inconsistent with known Allied technology. How could a heavy twin-engine aircraft accelerate so quickly and climb so effortlessly? Japanese engineers, who prided themselves on simplicity and efficiency, needed to understand how the Americans had built such a formidable engine system. In the autumn of 1943, opportunity arrived. A P-38G Lightning of the 39th Fighter Squadron made an emergency landing on a Japanese-held island in the Aleutians. The pilot was captured, the aircraft largely intact. It was carefully disassembled, packed into crates, and transported first to Japan by ship, then to Tachikawa Air Technical Arsenal, the center of Japanese aeronautical research, outside Tokyo. There, in Hangar Number 4, a group of Japan's leading engineers, metallurgists, and engine specialists gathered to examine the captured machine. When the crates were opened, the room fell silent. Before them stood an aircraft that looked like nothing they had ever built. The clean symmetry of the twin booms, the smooth surfaces, and the tightly packed central nacelle suggested not improvisation, but a deeply integrated design philosophy. Every cable, every hydraulic line, every piece of ducting had a purpose. It was a product of industrial order on a scale that Japan's fragmented war economy could scarcely imagine. The first step was to remove the two Allison V-1710-51 engines from their mounts. The Japanese engineers, familiar with radial engines like the Nakajima Sakai and Mitsubishi Kensei, were surprised by the compactness of the V-12 layout. The engine's crankcase and reduction gear housing were machined from aluminum alloy, with precision far exceeding what most Japanese factories could replicate under wartime conditions. The Allison's liquid cooling system was of particular interest, but Japanese fighters had relied almost exclusively on air-cooled designs, which were lighter and easier to maintain in the field, but limited high-altitude performance. The P-38's engines, with their glycol-based cooling system, could maintain optimal thermal balance at high manifold pressures, essential for turbocharging. The radiators, oil coolers, and intercoolers were arranged within the wing booms in a way that balanced drag and airflow perfectly. To the Japanese examiners, the internal ducting alone was a work of art. But what truly astonished them was what came after the engine, the General Electric B-13 turbo supercharger. Mounted behind each engine in the tail section of the boom, it used exhaust gases to drive a turbine wheel spinning at over 20,000 revolutions per minute. The turbine compressed intake air, which was then cooled in an intercooler, before entering the engine's supercharger stage. This two-step system allowed the V-1710 to maintain nearly full sea-level power at altitudes above 25,000 feet, a feat Japanese engines could not approach. As they examined the turbine assembly, the engineers found themselves facing an entirely new world of metallurgy. The turbine blades were forged from Inconel, a nickel-chromium alloy resistant to extreme heat. Japan had no equivalent material in mass production. Attempts to measure its exact composition revealed trace elements that hinted at manufacturing techniques beyond their reach. The bearings were sealed, finely balanced, and capable of sustaining enormous rotational speeds without failure. One Japanese metallurgist later remarked that even if they could copy the shape, they could not copy the metal. The exhaust piping leading to the turbocharger was double-walled, insulated to maintain energy efficiency, and featured expansion joints that compensated for thermal stress, something unseen in Japanese aircraft design. To the observers at Tachikawa, it was clear. The P-38's engine system was not merely advanced, it was the product of an industrial ecosystem of rare metals, precision tools, and specialized foundries. The Japanese had experimented with superchargers before, but exhaust-driven turbocharging was almost entirely alien to their engineering culture. The concept was understood theoretically, using waste exhaust gases to power a compressor, but the practical application was elusive. The materials required to withstand high heat and rotational stress were scarce, and machining tolerances necessary for stable operation were beyond wartime Japanese factories. At Tachikawa, the engineers tested the turbo unit carefully. They disassembled the casing, examined the turbine, and measured the clearances. They noted the subtle curvature of the impeller blades, and the precision of the wastegate mechanism that controlled boost pressure. The wastegate actuator, a small servo-driven valve, allowed the engine to self-regulate its turbo output depending on altitude and throttle setting, a level of automatic control the Japanese found remarkable. The entire system, from the exhaust manifold to the intake duct, formed a feedback loop controlled by manifold pressure regulators and pressure-sensitive valves. It was, in essence, a mechanical brain. The Japanese report on the captured P-38 stated that the aircraft's supercharging system exhibits extraordinary integration between engine and turbine, beyond domestic production capacity. In plain language, they could not build it. Their attempts to replicate the system, even on a reduced scale, failed. The turbine blades deformed under heat, bearings seized, wastegate valves cracked. Japanese metallurgy, limited by shortages of chromium and nickel, simply could not sustain the extreme environments inside a turbocharger. Moreover, the precision machining required for the small clearances between turbine and casing was beyond the capability of wartime tooling. To Japanese engineers, this revealed a deeper truth. The Americans had achieved not just technological innovation, but industrial depth. The turbocharger was more than a part, it was evidence of an entire supply chain, built for precision, power, and endurance. The P-38's turbo system represented an engineering philosophy that saw complexity as a means to performance, while Japan's design culture, constrained by material shortages, valued simplicity as survival. Beyond the engines, the Japanese examination extended to the P-38's control systems and instrumentation, the nervous system of the Lightning. They found that the pilot's throttle quadrant was linked by intricate cables to both turbochargers, allowing independent or synchronized control. Dual boost gauges, mixture controls, and intercooler shutters gave the pilot fine-tuned authority over the aircraft's breathing system. The cockpit, bristling with dials, seemed to the Japanese technicians both bewildering and awe-inspiring. They noted the presence of boost pressure regulators, thermostatically controlled oil radiators, and electrically driven fuel pumps, all systems requiring precision parts and complex wiring harnesses. Each element was interconnected, ensuring that the Allison engines performed reliably under the most demanding conditions. The report compiled at Tachikawa concluded that the P-38 embodies the industrial maturity of the United States. This was no mere observation, it was an admission of limitation. Japanese aircraft of the same period, such as the Ki-43 Hayabusa or A6M50, were marvels of aerodynamic simplicity, light, elegant, and deadly at low speed, but their power plants were products of a nation fighting against resource scarcity. The P-38, by contrast, symbolized abundance, abundant metal, abundant precision, abundant industry. As the Lightning systems were studied, one senior Japanese officer remarked that the aircraft seemed to have been designed by engineers who had never known constraint. Every component, from the stainless steel tubing to the redundant hydraulic pumps, spoke of a nation able to invest deeply in perfection. The officer's words, recorded in a post-war interview, reflected both admiration and frustration. When the examination concluded, the P-38 was reassembled as best they could, though it never flew again. The test data, drawings, and metallurgical samples were archived. Engineers used the findings to inform Japan's late-war turbocharger experiments, such as the Mitsubishi Ha-43, with experimental exhaust turbines, none of which entered full production before the war ended. In the years after the war, fragments of the Tachikawa study resurfaced. Among them were notes describing the Allison V-1710 as an engine ahead of its time. The report praised its smooth power delivery, durability, and especially its modularity, a design principle that allowed Allison to adapt the same engine core to many aircraft, from the P-38 to the P-40 and even early P-51 prototypes. But what left the deepest impression on the Japanese evaluators was not the raw power, it was the system integration. They had learned that the true gene the Lightning lay not in one part, but in the union of many. Engine, turbocharger, intercooler, ducting, control, and cooling all working in harmony. It was a living machine, not a collection of components. This systemic engineering, the idea of designing every element to serve the performance of the whole, was something that Japanese engineers would later emulate during the post-war decades of industrial reconstruction. When American occupation forces arrived in Japan in 1945, they found that much of the P-38's examination data had been preserved. U.S. intelligence officers were astonished to see detailed technical sketches of the Allison engines and turbo units, evidence of the respect with which Japanese engineers had studied their former enemy's technology. In many ways, that respect marked the beginning of Japan's post-war transformation into a technological powerhouse. The seeds of curiosity sown at Tachikawa would bear fruit in the jet age. The Allison V-1710 and its dual turbocharged configuration thus achieved something remarkable. It became a lesson in engineering philosophy. By 1943, the Pacific War had become a proving ground for technological evolution. Where once the nimble Mitsubishi Zero dictated the terms of aerial combat, now the balance was shifting. The arrival of the P-38 Lightning in the theater marked a new era, an aircraft built not for agility alone, but for power, altitude, and reach. From the first moment, Allied pilots took the P-38 into combat over the Solomon Islands. They felt the difference. Its twin Allison V-170 engines, each boosted by a General Electric turbocharger, delivered consistent thrust at altitudes where the thin air would have left most fighters gasping. Pilots could climb to 30,000 feet and still maintain speed and maneuverability. For Japanese aviators, accustomed to engines that lost much of their output above 20,000 feet, this was incomprehensible. In dogfights, the P-38's advantage was clear. It could dive faster than any Japanese fighter, and its turbo-boosted engines allowed it to reascend almost as quickly. American pilots learned to use the aircraft's altitude advantage as a weapon, striking from above, making a single devastating pass with its concentrated nose-mounted armament, then climbing out of reach. The Lightning's twin-engine configuration provided security on long missions. Even with one engine damaged, the aircraft could limp home. Yet behind every tactical success lay the invisible hand of engineering. The turbochargers gave the Allisons their resilience, compensating automatically for changes in air density and maintaining manifold pressure with uncanny precision. While Japanese mechanics adjusted carburetors and supercharger settings manually on the ground, Lightning crews simply checked the dials and flew. It was the technological embodiment of confidence, a machine that worked because every part had been designed to serve the whole. The Pacific Campaign reached its technological crescendo during the attacks on Rabaul in late 1943. Here, the P-38 faced the best Japanese defenses, seasoned Zero pilots, heavy anti-aircraft fire, and difficult weather. Yet it was during these missions that the Allison V-1710's dual turbocharging proved its worth most dramatically. Rabaul's airspace was often filled with towering cumulonimbus clouds that rose to 35,000 feet. Where most fighters struggled in the turbulence and thin air, the P-38's turbochargers thrived. The engines maintained smooth power as the aircraft climbed through the vapor walls, their twin exhausts glowing dull orange against the Pacific dawn. Pilots reported that even above the storm tops, their engines felt solid, unaffected by altitude. In one of the war's most famous missions, Major Thomas McGuire and Captain Richard Baum, both flying P-38s, used their altitude advantage to destroy multiple enemy aircraft before the Japanese could react. Their Lightning formations descended from the stratosphere with calculated precision, attacking from the sun's glare. Japanese pilots later recounted that the American aircraft seemed to appear from nowhere, striking with impossible speed and vanishing just as suddenly. What they could not see was the secret buried within those engines. Twin turbochargers, feeding twin intercoolers, keeping the Allisons cool and powerful, and air too thin for carburetors to function efficiently. The Japanese could outturn the Lightning at low altitude, but at 25,000 feet, where oxygen was scarce and air resistance thin, the Zero was helpless. The air over Rabaul became the proving ground for altitude power, and the Allison engine reigned supreme. Every pilot who flew the P-38 came to trust its engines like companions. In tropical heat, freezing cold, and even under battle damage, the Allison V-1710 proved astonishingly durable. This reliability was not coincidence. It was the result of deliberate engineering choices that combined redundancy with simplicity in critical systems. Each engine had independent fuel, oil, and cooling circuits, meaning one could fail without dooming the aircraft. The turbocharges were shielded within the tail booms, drawing heat away from the central nacelle. Even the exhaust paths were calculated to balance thrust and reduce turbulence along the tailplane. Maintenance crews loved the Allisons for their accessibility. Panels opened with precision-fit fasteners, Wiring looms were color-coded, and the turbo plumbing was arranged logically for quick servicing. Such attention to detail reflected the industrial philosophy behind American engineering, one where precision did not end on the drafting table, but extended to every rivet and gasket. Japanese airmen who had examined the P-38's captured engines could only marvel at this consistency. To them, an engine was often the sum of handcrafted parts fitted by skilled artisans. In contrast, the Allison was a product, standardized, repeatable, and perfect in duplication. Each engine that left the assembly line in Indianapolis was virtually identical, a triumph of mass precision. It was industrial power as art. This reliability gave the P-38 something rare in early war aviation: trust. Pilots flew farther, fought longer, and dared more because they believed their machines would bring them home. That psychological confidence was itself a weapon. Meanwhile, back in Japan, the lessons of the captured P-38 continued to ripple through the corridors of Tachikawa Air Technical Arsenal. The engineers, though unable to replicate the turbocharger technology, absorbed its philosophy. They began experimenting with exhaust-driven compressors on test stands, seeking ways to stabilize rotational speed. Some designs, such as the Nakajima Ha-44 and Mitsubishi Ha-43, explored multi-stage supercharging inspired by the Allison's intercooler concept, though none reached operational maturity. Post-war testimonies from surviving engineers reveal the deep impression the Lightning left. One recalled, "The P-38 showed us the difference between craftsmanship and system engineering. We had great designers, but they had an industry." That realization became a quiet foundation for Japan's future technological renaissance. The principles of integration and reliability, observed in the Lightning's turbo system, later appeared in the jet engines and industrial turbines developed during Japan's reconstruction in the 1950s. The study of the captured P-38 had not merely revealed the machine, it had revealed a philosophy. The Tachikawa examination was never meant to be homage, but it became one. Amid a brutal war, Japanese engineers had paused to admire the genius of their adversary, acknowledging a kind of mechanical beauty. It was a rare moment of respect between enemies, born from the shared language of engineering. When the war ended, the P-38 faded from the skies, replaced by faster jets and more advanced propeller aircraft. Yet the legacy of its twin turbocharged Allisons endured quietly. Engineers on both sides of the Pacific had glimpsed the future in that machine, the blending of power, altitude control, and thermal mastery that would define jet propulsion. In the post-war United States, General Electric's experience with the P-38's turbo systems fed directly into early jet engine development, including the J-33 and J-47 series. The control systems pioneered for the Lightning, wastegates, boost regulators, intercoolers, became the conceptual ancestors of jet fuel flow and temperature management systems. Every time a jet climbed effortlessly through thinning air, it owed something to the lessons first proven over Rabaul. For Japan, the captured Lightning was both humiliation and inspiration. The engineers who had studied it at Tachikawa went on to lead post-war industrial programs in metallurgy, precision machining, and power systems. Many cited that experience as their awakening to the scale of modern engineering. The respect they once held for the Allison's turbines transformed into a drive to master their own technologies. Today, when restorers fire up a surviving P-38, the twin Allisons roar with the same clean precision they did 80 years ago. Each turbine still spins in harmony. Each duct still breathes the balance of air and fire conceived by engineers who dared to solve complexity. The Japanese once called it impossible to imitate. And perhaps that is true, not because others could not copy the parts, but because they could not copy the spirit of the system that gave them life. The Allison V-1710 and its General Electric turbochargers were more than machines. They were proof that innovation, when joined to industrial mastery, could shape the fate of nations. In the end, the Lightning's greatest victory was not in combat, but in what it taught the world: that engineering, when pushed to its limits, becomes something close to art. By the final year of the war, the P-38 Lightning had become an icon of the Pacific. Its long, elegant wings and twin tails could be seen from the Philippines to Okinawa, escorting bombers and hunting enemy aircraft in skies once dominated by Japan. The very technology the Japanese engineers had examined in secrecy at Tachikawa was now breaking their defenses in open daylight. The Allison V-1710, refined through successive variants, continued to perform under punishing conditions. Even as tropical humidity corroded metal and heat warped aluminum, the turbocharged engines delivered steady power. Pilots trusted them utterly. When one engine failed, the other carried the Lightning home, sometimes over hundreds of miles of ocean. That dual-engine reliability became a metaphor for Allied perseverance, balance, endurance, and strength through design. By 1944, the Lightning had matured into a formidable long-range escort and reconnaissance platform. In missions, such as Operation Vengeance, the assassination of Admiral Isoroku Yamamoto, the aircraft's range and high-altitude capability proved decisive. It was the only fighter in the Allied inventory that could undertake a mission of that distance, over 400 miles each way, and still fight when it arrived. The success of that mission was a testament not merely to skill, but to the profound mechanical confidence built into every component of the Allison engines and their turbocharging systems. As the war drew toward its close, the P-38 began to give way to newer designs, such as the P-51 Mustang and the twin-jet P-80 Shooting Star. Yet even as newer technologies eclipsed it, the Lightning remained revered among pilots as a machine that had done the impossible, conquering both the tyranny of distance and the thin, hostile air of the upper atmosphere. When Japan surrendered in August 1945, the victorious Allies began an immense technical survey of the defeated nation. At Tachikawa Air Technical Arsenal, they discovered something extraordinary: the detailed examination reports of the captured P-38, in bound volumes filled with precise sketches and meticulous measurements. Japanese engineers had documented everything, from the shape of the turbine blades to the chemical analysis of the alloys. The American investigators were astonished. The level of detail was almost forensic. The Japanese had disassembled the aircraft with scientific precision, cataloging every pipe, duct, and valve. They had even performed heat resistance tests on small turbine fragments, documenting their results in neat kanji script. To the Americans, it was an unexpected tribute. The enemy had admired their machines so deeply that they had tried to understand it down to the molecular level. The recovered documents were shipped back to the United States, where they became part of the Air Technical Intelligence Archives. There, historians and engineers pored over them, not as intelligence but as a record of respect. They revealed how far ahead Allied metallurgy and mass production techniques had been, and how closely Japan had come to understanding them, even without the means to replicate what they saw. These reports later provided valuable data for historians studying the technological disparities between the wartime powers. They also offered something more profound: evidence that even amid total war, curiosity and admiration could transcend hostility. The engineers at Tachikawa had not been saboteurs. They had been students of excellence. The lessons of the Allison and its turbochargers did not vanish with the end of piston engines. On the contrary, they became the stepping stones to the jet age. General Electric, having mastered high-temperature metallurgy for the Lightning's turbines, was now poised to build America's first operational jet engines. The same alloys, the same heat-resistant seals, and the same understanding of airflow dynamics all fed directly into early turbojet development. The GE I-40 and J-33 engines were direct descendants of the principles proven in the P-38. Engineers who had designed the B-13 turbochargers for the Lightning became pioneers in axial flow turbine design. They understood, perhaps better than anyone, that the management of heat, pressure, and flow was the key to sustained high-altitude power, the very lessons first taught by the Allison system. In Japan, similar transformations began under American occupation. Many of the engineers from Tachikawa later joined the new industrial firms that would rebuild the nation: Mitsubishi Heavy Industries, Nakajima's successor Fuji Heavy Industries, and later Ishikawa Yamaharama. Their wartime exposure to Allied turbo systems gave them a blueprint for post-war progress. The meticulous discipline they had shown in studying the P-38 evolved into a national obsession with precision manufacturing. By the early 1950s, Japan was producing its own jet engines, small at first but increasingly refined. Each was, in a sense, a descendant of that single captured P-38, a living echo of the day Japanese engineers first looked inside an Allison V-1710 and understood how far human ingenuity could go. Decades later, As surviving P-38s were recovered from remote jungles and frozen lakes, engineers and restorers faced the same puzzles that had once fascinated the men at Tachikawa. The twin-turbo supercharging system, with its network of ducts and regulators, still inspired awe. Even with modern tools, restoring those engines required a level of craftsmanship and understanding that bordered on reverence. At Chino, California, and Duxford, England, restoration crews disassembled the engines with the care of archaeologists. Each polished turbine blade, each intercooler duct, told a story of foresight and precision. Modern metallurgists studying surviving parts confirmed what the Japanese had discovered. The alloys used in the turbine housings were exceptionally advanced for their time, with trace elements that improved fatigue resistance and oxidation control. When a restored P-38 takes flight today, its engines produce the same clean, confident sound that once echoed over the Pacific. The turbochargers whine faintly at altitude, the propellers beat in perfect synchrony, and the aircraft's long silver wings slice through air that once belonged to history. Observers often describe the sight as haunting, not just for its beauty, but for the realization that human hands built something so enduring in the midst of war. Every flight is a tribute, not only to the American engineers who created it, but to those who once studied it in awe. In a sense, every restored Lightning carries two legacies: the ingenuity of its makers and the respect of those who once sought to understand it. In the end, the story of the Allison V-1710 is not merely about horsepower, metallurgy, or aerodynamics. It is about philosophy, about how nations think when they build machines. The Americans built the V-1710 and its turbo system not just to win a war, but because they believed in the power of integration, of systems working in harmony. It was an engine that reflected confidence in technology itself, faith that complexity could be mastered and made reliable. The Japanese, when they examined the captured P-38, saw more than a machine, and they saw a culture of precision, an industry capable of organizing thousands of people and processes toward a single, flawless result. Their admiration for that achievement was genuine. In their notes, they described the engine as an elegant mechanism of continuous power. Even amid devastation, that phrase captured the essence of what they had seen: not an enemy's weapon, but a triumph of human intellect. Decades later, as historians looked back, they realized that the encounter between the P-38 and its examiners at Tachikawa was one of the quietest but most profound moments of the war. It was a meeting not of soldiers, but of minds, of two civilizations separated by conflict yet united by a shared reverence for engineering beauty. Today, the roar of the P-38 Lightning still echoes across air shows and documentaries. To hear its twin Allisons thunder in harmony is to hear the heartbeat of an era, the age when metal, fire, and thought combined to reach for the edge of the sky. It is the sound of invention itself. If this video was worth your attention, it would help to like the video and subscribe to the channel, so more videos about aviation marvels be brought to you.